Hello and welcome to Mike Academy. So in today's video we are going to be looking at error analysis, and much later on in the video we are going to be delving into error propagation. Now, error analysis is basically identifying, quantifying and reducing error which are due to measurements or calculations using numerical techniques. Now, there are different types of error that could occur when taking measurement or calculations. We have what is called the inherent error, we have the truncation error, we have the round-off error, we have the absolute error, we have the relative error, and we have the percentage error, and many more. But in this video, we are going to be paying attention to the absolute error, the relative error, the percentage error, and error propagation. Now, let's start with absolute error. Okay, let's start with absolute error. Now, let's assume, or let's say, let capital X be the true. Let capital X be the true value of a quantity. Let capital S be the true value of a quantity without an error. And let small x be the approximate value. Let small x be the approximate value of the quantity, or of that quantity. Now, when we say approximate value, it simply means the original value has either been reduced by subtraction or by round off. So let capital X be the real value or true value of a given quantity without an error. Let small x be the approximate value of that quantity. That simply means in this case there's an error. Now, the absolute error, which is AE, is simply going to be equal to the modulus, or the modulus of the true value minus the approximate value. The true value minus the approximate value. So in this case, we called capital X to be the true value and we called small x to be the approximate value. So this simply implies that absolute error AE is simply equal to capital X, the modulus of capital X minus small x. And if you obtain this is simply called the absolute error. So that's how you calculate the absolute error of a given function. Simply the modulus of the true value minus the approximate value. Now, if this is the absolute error, then the next thing we can talk about is what is called the relative error. What is the relative error? Okay, the relative error is simply the ratio of the absolute error to the modulus of the true value. It's simply the ratio of the absolute error to the modulus of the true value. So that simply means that relative error is equal to absolute error modulus all over the modulus of the true value. Okay, so in this case now we considered capital X to be the true value. So this simply implies that our relative error R dot E is equal to, now recall, our absolute error gave us modulus of the true value minus the approximate value. So you simply have modulus of the true value minus the approximate value divided by modulus of the true value, and this gives us what is called the relative error. Now, the third type of error we talk about is the percentage error. Okay, percentage error. The percentage error is simply by multiplying the relative error with 100%. So percentage error is simply equal to relative error multiplied by 100%. This is how you obtain your percentage error. Now, let's pick some few examples to explain this concept before we go deep into error propagation. Let's pick some few examples. Welcome back. So we have two questions on the board. Let's consider this question to explain everything we've learned here so far. Now, the very first question says, round off the number 978620 correct to 4 significant figures and calculate the absolute error, the relative error, and the percentage error. Okay, so I have put out this formula for the absolute error over here, but keep in mind, absolute error is always the true value minus the approximate value. So for that given question, all we need to do is pick out our true value, then pick out our approximate value, then take the modulus of their difference. That becomes our absolute error. So considering the first question, it says round off the number 978620. So that means our true value, the true value, which is capital X, is equal to 978620, and we are to round off this number to 4 significant figures. Mind you, this is 1, 2, 3, 4, 5 significant figures, so you don't count 0 after a number. You don't count the 0 at the end as a figure. It's not counted as a figure. So instead of 1, 2, 3, 4, 5, 6, it's actually 1, 2, 3, 4, 5, and we are actually round this off to what? 4 significant figures, so which means we need to end at 1, 2, 3, 4. Now that round off is called the approximate value. Now our approximate value, the approximate value, which is small x, is obtained by rounding off this true value. Now rounding off simply means you're going to convert this 2 to 0, because into 4 significant figures we have 9786, so this is enough to give us 4 significant figures. Therefore the number in front of the 6 is automatically rounded off to 0. So you simply have 9786, the 2 in front becomes 0, and then you have 0. So this becomes our approximate value. Now the absolute error, remember the absolute error AE, we said it is simply what? The modulus of the true value minus the approximate value. So this is equal to modulus. True value is given as this 978620 minus our approximate value gave us this 978600. Now if you do this subtraction, you're going to obtain that your absolute error is going to be equal to the modulus of 20, and modulus of 20 still remains 20. So this remains our absolute error. Now the next question says we should calculate the relative error, and I said relative error is given simply as the modulus of the absolute error, okay, divided by the modulus of the true value, capital X, where capital X represents the true value. So this is going to be equal to the modulus of the absolute error is simply mod 20, and mod 20 still remains 20, divided by modulus of the true value, and this is the true value. So modulus of 978620, okay, so this modulus still remains, this is 20 divided by 978620. So always keep it in mind, whenever you take the modulus of any number, it becomes the positive value of that number. So the essence of modulus is to make sure if there's any negative sign, the modulus will eliminate the negative sign. That's the essence of modulus. Okay, so our relative error is now going to be equal to, so let's find 20 divides 978620. So that gives us approximately 0.0000204. So this becomes our relative error. Okay, so this becomes our relative error. Finally, we are asked to calculate the percentage error. So the percentage error, we said it is simply going to be the relative error multiplied by 100%. So this simply implies that our percentage error is equal to, our relative error on the board is 0.0000204, multiply this by 100%. So this simply implies that our percentage error is going to be equal to, that becomes 0.00204%, and this is our percentage error. So that's how you calculate the absolute error, the relative error, and the percentage error when you're given to round off a given function. Now let's consider the second question. The second question says approximate the derivative of sine x as x equals pi all over 4, using the central difference method with step size h equals 0.01 and calculate the absolute error, relative error, and the percentage error. Okay, so let's get here all wiped up. Alright, so carefully read the second question to properly understand. It says approximate the derivative of sine x at x equal to pi all over 4 using the central difference method. So approximate that derivative using the central difference method. So this simply means that the approximate value of that derivative should be obtained using the central difference method. So when we use the central difference method, any value we obtain there for that derivative becomes the approximate value. Now, not forgetting we are given our function f of x was given to us simply to be sine x, and we're given at x equals pi all over 4. So first we find our true value. So the true value which is capital X is equal to, now it becomes the derivative of this function at this point pi all over 4 without using the central difference method. So when you use the central difference method, that becomes the approximate value from what the question is saying. Okay, so which means true value x is obtained by looking for what? F prime of x at x equals pi all over 4. So which means we find the derivative f prime of x, find the derivative of this function. If I differentiate sine x, I will simply have cos x. So that simply means now that f prime at pi all over 4 is going to be equal to cos, in place of x, putting the value as pi all over 4. And in front of a 3 function, pi always appears as 180 degrees. So which means pi over 4 simply means 180 divided by 4, and that will simply give you 45 degrees. So that means this is actually what? Cos 45. So which simply implies that f prime at pi all over 4 is simply equal to cos 45 gives us 0.7071. Hence our true value x is what? F prime of x at x equals pi all over 4. So this simply implies that the true value capital X is going to be equal to 0.7071. Alright, so this gives us our true value. Now from the question, approximate that derivative using the central difference method. So which means we are going to now employ the central difference method to find the approximate value. Okay, so the central difference method is given. Central difference method is given. Okay, as f prime of x to be equal to f of x plus h minus f of x minus h all over 2 times h, where h is given simply as a step size, and in the question we are given a step size of 0.01 for h. Okay, but this is now our central difference method, so which means value obtained from this derivative is simply taken as our small x, which is called the approximate value. So let's find now, we need to find f of x plus h. Therefore f of x plus h is equal to, the function itself, remember, is sine x, so that becomes sine. Now we are increasing the x by h. Okay, so that becomes sine x, and x itself is what? X was given to us as pi all over 4, so you have pi over 4 plus h, but h was given in the question, that is the step size. H was given simply as 0.01, so you have plus 0.01. okay, so f of x plus h is now going to be equal to, this is sine. Now recall that pi over 4 is something as 45, which is 180 divided by 4. Okay, so you have 45 plus 0.01. So this simply implies f of x plus h is going to now be equal to sine 45.01. So let's obtain sine 45.01. This will simply give us 0.7072. Okay, next thing from the formula we find f of x minus h. Okay, so f of x minus h is now going to be sine x remains pi all over 4 minus h remains 0.01. So f of x minus h is going to be equal to sine, not forgetting pi over 4 simply means 45 minus 0.01. okay, so f of x minus h is going to be equal to, this becomes sine 45 minus 0.01 simply gives us 44.99. so therefore this simply implies that f of x minus h is going to be equal to, let's find sine 44.99, and that will give us approximately 0.7070, and we have this. Now, having found f of x plus h and f of x minus h, we can now plug it into this formula and obtain the approximate value. So I think we can use here now. Okay, so the approximate value x is now going to be equal to, from the formula, remember, f of x plus h minus f of x minus h, and f of x plus h simply gives us here as 0.7072. so you have 0.7072 minus f of x minus h, that gives us here as 0.7070. so you plug it in, you have 0.7070 divided by 2 times h, that's 2 times h itself is 0.01. okay, so approximate value x is equal to, now 0.7072 minus 0.7070, this gives us 0.0002 divides 2 multiplies 0.01, this gives us 0.02. now if 0.0002 divides 0.02, you have this value to be equal to 0.01. okay, so this simply implies that our approximate value x is 0.01. now, having found your true value and your approximate value, let's now start our error calculation. We start by absolute error. The absolute error, remember, is the modulus of the true value minus the approximate value, and this is equal to modulus of the true value itself gives us 0.7071. so you plug it in, you have 0.7071 minus the approximate value gives us 0.01, so minus 0.01. so this simply implies that our absolute error is equal to modulus of, now let's obtain 0.7071 minus 0.01, that gives us 0.6971, and of course the modulus of 0.6971 still remains 0.6971. so this becomes the value of our absolute error. Okay, having found the absolute error, the next thing to find is the relative error. Our relative error, ROE, remember, is the modulus of the absolute error divided by the modulus of the true value. So this is going to be equal to modulus of the absolute error gave us here as 0.6971. You have 0.6971 all over the modulus of the true value. True value itself is 0.7071. If you take the modulus of 0.7071, you still have 0.7071. so that simply gives us over here 0.7071. so let's find this division. This is going to be equal to, let's find 0.6971 divided 0.7071. this gives us approximately 0.99. okay, so this becomes our relative error. Finally, we calculate our percentage error. Percentage error is obtained by multiplying the relative error with 100%. okay, so which means our percentage error is equal to relative error by 100%, and that is simply equal to 0.99 multiplied by 100%, and as such our percentage error is simply 99%. okay, so that's how you calculate the relative error, absolute error, and percentage error using those two questions. Now, in the next segment of this video, which we are about to start, we are going to be looking at error propagation. There are several ways of propagating error. You can propagate either by addition, subtraction, division or multiplication. And in this video, we are going to be covering propagation by addition and subtraction. Then in the next video, we are going to be looking at error by division and multiplication with a couple of examples. Okay, so let's begin the second segment of the class. Alright, welcome back. Now let's talk about error propagation by addition. Supposing capital Z, okay, supposing capital Z is a quantity defined by the addition of two quantities, capital X plus capital Y. Okay, supposing capital Z is a quantity defined by the addition of two quantities, capital X plus capital Y, and this indicates the true values. Okay, this indicates true values. So with the capital letters, we are simply indicating the true values. Now, also supposing small letter Z is equal to small letter X plus small letter Y, indicating the approximate value of this given function. So this indicates the approximate value. Okay, this indicates the approximate value of this given function Z. Alright, whereas X indicates the approximate value of what? Capital X. Small y indicates the approximate value of capital Y. Okay, we said earlier that when we want to calculate the absolute error simply means the modulus of the true value minus the approximate value. Now let's say we want to find the absolute errors in this quantity. Okay, let's say we want to find the absolute error in Z, X, and capital Y. Let's say we want to find the absolute error. Now from our definition of absolute error, that means error in Z, so let's call that EZ. The absolute error in Z, remember, is going to be the true value of Z minus the approximate value of Z. So true value of Z is capital Z minus the approximate value of Z is what? Small z, and you have this. So which means from here we can actually make Z the subject of the formula. If we do that, you're simply going to obtain that capital Z is going to be equal to, let's send the approximate value of Z over here. It becomes the error in Z plus the approximate value of Z, which is the small z. So we'll have error in Z plus small z. So this becomes the value of our capital Z. Similarly, the absolute error in X, called as E capital X, is going to be equal to, remember, the true value, which is capital X. So you have capital X minus this, the approximate value, which is small x, minus small x. So this simply implies, just like in the first case, if I want to look for my capital X, this simply becomes, as the true value now, capital X simply becomes the error in X plus the approximate value. So if I simply send negative X over here, it becomes plus X, and X there is the approximate value. So we have error in X plus approximate value of X. And finally, the error in quantity Y is going to be equal to the true value of quantity Y, which is capital Y, minus the approximate value of quantity Y, which is small y. So this simply implies that I can find my true value of Y, which is capital Y, to be equal to error in Y. It becomes EY, okay, plus, if I move the approximate value now, negative Y over here becomes positive. So I have plus Y, which is the approximate value. Now let's plug all these values of things into this equation. We have that capital Z is equal to capital X plus capital Y, which are what? The true values. But we obtain, in terms of error, our true value for Z is given as EZ plus small z. So we have, in place of Z, we have the true value to be what? Error in Z plus the approximate error in Z, and this is equal to capital X means the true value of X, and we obtain the true value of X as error in X plus the approximate value of X. So we have EX plus approximate value, okay, this is for X, plus for Y. We also obtain error in Y plus the approximate value of Y. That is simply EY plus, okay, plus Y, and you have this. So error in Z plus the approximate value of z is going to be equal to, this is ex plus x plus ey plus y. Now let's send the approximate value of z, not forgetting this is the approximate value of z. Send the approximate value of z over to this side of the equation. Therefore you have that error in z is going to be equal to error in x plus error in y plus y. Now if I send the approximate value of z over here, remember it is positive here, so positive cross an equal sign becomes negative, so I have minus small z, which is the approximate value of z. So the error in that quantity z is going to be equal to error in x plus small x plus error in y plus small y minus, not forgetting we said the approximate value of z is equal to small x plus small y. So in place of z, we simply have x plus y. So error in z is equal to error in x plus approximate value of x plus error in y plus approximate value of y. If you expand this bracket, you have negative times x becomes negative x. Again, negative times y becomes negative y. So this simply means that error in z is equal to error in x. Observe that plus x minus x cancels out and plus y minus y cancels out. So I'm left with error in x plus the error in y. And of course, if you take the modulus on both sides, the modulus of error in z is going to be equal to the modulus of error in x. Okay, error in x plus error in y. Okay, it becomes the modulus of error in x plus error in y. And if you define a triangular inequality, then you're going to be having that the modulus of the error in z is going to be less than or equal to, introducing a triangular inequality becomes less than or equal to error in x plus error in y. Now this simply means that if you have a quantity that is adding and you're being told to find the absolute error of that quantity upon addition, the absolute error of that quantity that is adding is simply what? The sum of the errors of the individual quantities adding together. So we are going to pick an example to explain what this means. Okay, welcome back. Now let's consider this question on the board to explain error propagation by addition. Now the question says calculate the absolute error, relative error and percentage error in the quantity z equals root 2 to the power of 3 plus root 7 to the power of 3 correct to 4 significant figures. Okay, so we are given z to be equal, as capital Z now please, to be equal to root 2 to the power of 3 plus root 7 to the power of 3. Not forgetting, when we made this derivation, we simply called z to be equal to capital X plus capital Y, which indicates true value. So we're still going to basically use that same approach here. Okay, so but z equals capital X plus capital Y, where capital X and capital Y are the real values. So which means upon comparison, the real value for x is going to be equal to what? Square root of 2 to the power of 3, and the true value for capital Y is going to be equal to square root of 7 to the power of 3. Now remember, when we derive the error in z, we simply said it is simply the error in x plus the error in y. If the functions are adding, then their error simply means, or the error of that given quantity is the individual errors of the function. So if we have capital X to the true value to be this and capital Y true value to be this, then we need to find the approximate value of this x and y. And approximate value is what? Small letter x and small letter y. So let's first find the true values. True values now. True values. Okay, for capital X, we simply find square root of 2 to the power of 3. That becomes our true value. Okay, so let's find square root of 2 to the power of 3. Okay, so the true value of root x to the power of 3 simply gives us 2.828 427125. This is our true value. But from the question, it says correct to 4 significant figures. So which means the approximate value of x, approximate value of x, that becomes our small x. So we approximate this to 4 significant figures. By 4 significant figures, please take note, it's not 4 decimal place, but 4 significant figures. So which means when you count from here, you should count up to 4 places. So we start from 2, which is 1, 2, 3, 4. So that means by 4 significant figures, we have 2.828, and it ends there. So this is 1, 2, 3, 4. This becomes our approximate value, which is now the small x. So remember, error in x. So to obtain error in x, it means what? The true value minus the approximate value. This gives us the error in x. So that satisfies this. Now then, next is to find the error in y. So we know the value of y. The true value of y is this. We'll find the true value, find the approximate value, then subtract them. If you add the two of them together, that gives you the error in that quantity, c equal to this. Okay, so we can continue here. All right, so the true value of y, the true value of y is equal to the square root of 7 to the power of 3. So this simply implies true value of y is going to be equal to, so let's obtain the square root of 7 to the power of 3. Alright, so the true value of y, which is root 7 to the power of 3, simply gives us this 18.52025918, and we are asked to correct this up to 4 significant figures. Again, the approximate value, okay, the approximate value, which is small y now, is now going to be equal to, so this is 118 already, is 2 significant figures, so you have 1, 2, 3, 4, it ends in 52, which is now 18.52. This gives us 1, 2, 3, 4 significant figures. So this becomes the approximate value of y. So we know the approximate value of x, we know the approximate value of y. Now we can find the error in x. Therefore, error in x, called as EF, we simply said is going to be modulus of the true value of x minus the approximate value of x. This is going to be equal to modulus of the true value of x, simply give us this 2.8284272125. Okay, so we'll have 2.8284, then we have 27125 minus the approximate value of x, that gives us 2.828, okay, minus 2.828. all right, so this is now our error in x. This simply implies error in x can simply be written as, let's obtain this difference and see, that gives us 0.000, we have 424 approximately. Okay, so the modulus of this function still remains. This simply implies that error in x is going to be equal to 0.000424. This becomes our error in x. Okay, the next thing to do is to find the error in y. We can do that here. So error in y, EY, is simply going to be the modulus of the true value of y minus the approximate value of y. So error in y is going to be equal to the true value of y. We obtain the true value here as 18.52025, 18.52025, okay, 918 minus the approximate value we obtain 18.52, and we have this. So this simply implies that the error in y is given simply as mod. Let's obtain this difference. That also gives us 0.000259. okay, so this simply implies that our error in y is equal to 0.000259. Now, if you know your error in y, and you know your error in x, then you can compute the error in the function or quantity z. Therefore, error in z is simply equal to modulus of the error, okay, error in x plus error in y. So the error in z is going to be equal to error in x. We obtain the value as 0.000424. So you have 0.000424 plus error in y, which we obtain over here as 0.000259. Okay, so this simply implies that the modulus of the error in z is going to now be equal to, let's find this addition. This gives us 0.000683. Okay, so approximately the error in z also remains, because the modulus of this value still remains this value. We have 0.000683. okay, all right, so this becomes the modulus of the error in z. So this is the value of the error in z. So in essence, whenever two functions or two quantities are adding one another and you're asked to find the error in that quantity, the error is simply the sum of the individual error that makes up that summation. Okay, the sum of the individual error of the quantities that makes up that summation. So if you have up to 3 quantities, let's say z is equal to x plus y plus w, something like that. So far there are 3 in number and they are adding. All you need to do is find the error, individual error in each of them, and sum them up together. That becomes the error in that becomes the absolute error in that function. Now the next question says we should find the value of the relative error. And relative error, like I said, relative error is simply given as the modulus of the absolute error in z all over the modulus of the true value of z, which means we need to find the true value of z. Since we know the absolute error in z, we need to find the true value of z. Okay, and from here we are given that z is equal to root 2 to the power of 3 plus root 7 to the power of 3. So this simply implies that the true value of z, okay, true value of z is now equal to, so we find the sum of root 2 to the power of 3 and root 7 to the power of 3. So I'm going to be pointing all together at once. Do well to point along with me to avoid any calculation error, and if you spot any calculation error, feel free to post in the comment section. Okay, so let's find root 2 to the power of 3 plus root 7 to the power of 3. Okay, so that value gives us 21.3486863. Now let's take a look at the value we obtained for the absolute error in z. For the absolute error in z, we had 0.000683, which means the absolute error is approximated to 4 significant figures. Okay, the absolute error, as can be seen here, is approximated to 4 significant figures. As such, we also approximate the true value to 4 significant figures, and doing that, 21 is already 21 over here is already 2 significant figures. That means we have to approximate 4. Okay, we have to end at 34. But then the approximate value to 4 significant figures of z becomes, so you start from the very end. If you approximate 3 or you round off 3, you have 6. If you round off 6, that means 8 becomes 9. If you round off 8, that means 6 here becomes 7. If you round off 6, 8 here becomes 9. If you round off this 8 or this 9 now, this 4 automatically becomes 5. So to 4 significant figures, the true value of z is given simply as 21.35. This becomes the true value of z. Since the absolute error in z gave us in 4 significant figures, that means we are going to find the sum or the true value of z in 4 significant figures. And in 4 significant figures, we simply have 21.35. That becomes the true value of z. Okay, so therefore, the relative error becomes the absolute error in z, which gave us this 0.000 okay 683 divided by the true value of z, which is 21.35. So this simply implies the relative error in Z is now going to be equal to, now let's find this ratio and see. So 0.000683 divided into 1.35 simply gives us 0.0000. We have 3, 2, 0. Okay, so this becomes the relative error in Z. So this becomes the relative error in Z. Okay, having found this, the final question says we should find the percentage error. So percentage error in Z, remember, is going to be the relative error in Z multiplied by 100%. So this simply implies our percentage error in Z is now going to be equal to relative error gave us this 0.000320 multiplied by 100%. Okay. So this simply implies our percentage error in Z is going to be equal to, so if you multiply by 100, of course 2 of these zeros is going to be off, so we simply have 0.00320%. so this becomes the value of the percentage error in Z. Alright guys, so for that given question, or whenever you're given a quantity which is adding or summing, then we simply say that the absolute error in that quantity is simply the summation of the individual error that makes up that summation. Okay guys, so that's it for that question. Now let's move to error by subtraction, propagation error by subtraction. Now let's say supposing capital Z is a true quantity of two functions, capital X minus capital Y, subtracting one another. So these are my true value. Okay, these are the true values, and the approximate values become small z equals small x minus small y. So these are my approximate values. Okay, these are my approximate values. Now if I want to find the error in all the functions, so error or absolute error, so let's say we want to find the absolute error in value. So for Z, error in Z, okay, for error in Z, this is going to be equal to, so remember, for Z, error becomes the true value minus the approximate value. So I have the true value, which is capital Z, minus the approximate value, which is small z. So which means I can make my capital Z, which is the true value, subject of the formula. This simply implies that my true value is going to be what? Error in Z. If I move negative Z over here, it becomes positive. It becomes error in Z, okay, plus the approximate value of Z. Similarly, if I want to find the error in X, it's still going to be the true value of X minus the approximate value of X. So this simply implies that my true value of X, which is capital X, becomes error in X plus the approximate value of X. So I have error in X plus the approximate value of X. And finally, if I want to find error in Y, this becomes the true value of Y minus the approximate value of Y. So this simply implies, in order to obtain the true value of Y, which is capital Y, this is going to be what? Error in Y plus the approximate value of Y. So I have error in Y plus the approximate value of Y. Now let's plug all of this into this equation. Okay, all right, so in place of the true value of Z, we obtain error of Z plus the approximate value of Z. So in place of that, we have error of Z plus approximate value of Z, which is small z, and this is equal to, we said, the true value of X. And what is the true value of X? We obtain it here as error in X plus the approximate value of X. So we have error in X plus approximate value of X. Okay, this minus this minus. Now let's plug in. We have minus y, the true value of y, and the true value of y is error in y plus the approximate value of y. So we have error in y plus the approximate value of y. Now error in z plus the approximate value of z is now equal to error in x plus approximate value of x. Now let's expand this bracket with negative sign. So I have negative error in y, okay, minus the approximate value of y. Okay, so let's send z over to this side of the equation. We are going to have that error in z is now going to be error in x plus the approximate value of x minus error in y, okay, minus the approximate value of y. Now if positive z cross over, it becomes negative z. So you have this, but not forgetting the approximate value of z we obtain here, or is given here as x minus y. These are the approximate value of z. So that simply means that error in z is going to be error in x plus approximate value of x minus error in y minus approximate value of y minus, in place of z we have x minus y, and you have this. So let's expand that bracket with negative sign. Error in z equals error in x plus approximate value of x minus error in y minus approximate value of y. Negative expands this bracket will have negative x, negative times negative y becomes positive y. You have this. So error in z is equal to error in x. Now observe that plus x minus x actually cancels out. Again, minus y plus y also cancels out. So I'm left with error in x minus error in y. But not forgetting to always take your modulus, because the error is a modulus function. So if you take your modulus, the modulus of error in z is going to be equal to the modulus of error in x plus the modulus of negative error in y. So this means that the modulus of error in z is going to be equal to the modulus of error in x, okay, plus the modulus of negative error in y becomes positive. So you have plus modulus of error in y. Now this is the same thing as what we obtained for the addition. So when a quantity is being added, when two or more quantities are being added and you're asked to find the error, all you need to do is what? Find the absolute errors by taking the difference between the real value of this quantity and their approximate value. Then you add them together. In this case, whenever the two quantities are also subtracting one another, you observe that the same error equation holds for the two. All you need to do is what? Find the error function in one of the values subtracting and add the error function in the other value which it is subtracting. Okay, so the error by subtraction and error by addition basically gives you the same result and no difference. So for the question we solved earlier, if you are to be a negative value, let's say root 2 to the power of 3 minus root 7 to the power of 3, in that case you still obtain the same result as what you obtained when it was root 2 to the power of 3 plus root 7 to the power of 3, simply because the equation for the both of them are the same. Okay, so let's just proceed. So you simply obtain that the error, so if we introduce our triangular inequality, we have that the error in z is going to now be equal to, is going to be less than or equal to the error in x plus the error in y, and you have this. So which means if you want to find your this is now your absolute error. If you want to find your relative error, remember becomes the absolute error, which is error in z divided by the true value, the modulus of the true value, which is modulus of z, and you have z becomes your relative error. And if you want to find the percentage error, simply multiply this by what? 100%. So it's as simple as this. For that same given question, let's say the quantity z is equal to root 2 to the power of 3 plus root 7 to the power of, okay, minus root 7 to the power of 3. Now this result is the same result as what we saw for earlier. Okay, so it would have still given us the same result, simply because whenever you're subtracting a quantity and you have to find the absolute error in that quantity, the same rule that governs the absolute error by addition is the same rule that governs the absolute error by subtraction. So whether addition or subtraction, you're still going to obtain the same result. Now let's pick an example to also explain this concept. Alright, so let's consider this question on the board. The question says calculate the absolute error, the relative error, and the percentage error correct to 4 significant figures for the following quantity: root 3 minus root 2 minus root 5. Okay, so I'm going to be leaving this as a practice problem for you. Just lay your hands on it, and if you're able to solve it correctly, you can post the answer in the comment section, or you can share to my WhatsApp number right there on the screen, and I'm going to verify it for you. But just to give you a hint, as explained earlier, just simply say let the quantity z be equal to root 3 minus root 2 and minus root 5. So you can simply recall that z in this case is going to likely be x minus y minus w. So you assign x to root 3, assign y to root 2, assign w to root 5, then find their absolute error by taking the difference in true value and difference in the approximate value. You can just lay your hands on it. Alright guys, so that's it on error analysis. In the next video, we are going to be looking at error analysis or propagation by multiplication and division. I hope to see you in that video. Do well to like the video, comment nicely, share to your friends, and if you're new to the channel, do well to also subscribe to the channel in order not to miss out on subsequent videos that will come out on numerical methods. I hope to see you in our next video. Thanks.